So now what we're going to do is we're going to find the critical point and then determine the extreme values, and we've got this mess of an equation here. All right, so we've been given some parameters. X has to be greater than or equal to 0. And y is equal to x to the 2/3 times x squared minus 4. So no matter what we do, we have to take the double derivative. So y prime means that we're going to have to employ the product rule. So when we say uv prime, we really say uv prime plus vu prime. So y prime then is u left alone, which is x to the 2/3, times the derivative of this stuff, which is just 2x. All right, plus this stuff left alone, which is x squared minus 4 times the derivative of this stuff, which is 2/3 x to the negative 1/3. Is that right so far?
Yeah.
Oh man, that's not very good. So then, what are the critical points for that? Well, I'm going to cheat a little bit. I'm just going to graph this thing. Okay? Can I do that? You guys mind? So what we're going to do is we're going to graph that. I mean, I could do the algebra, but you guys are going to take a test, and I'm assuming that you know that we would clean up the other side. We try to find a common power of x that would eliminate one of those. For example, we have a net x raised to the negative 1/3. So maybe I would multiply every term by x raised to the positive 1/3, right? And that would give me x to the 0, and we'd eliminate one term. And so we'd have like y prime equals 1 product of x, and that's easier to solve. We're going to skip all that for today. So what I'm going to do is I'm going to graph this thing. And I'm just going to say x raised to the 2 divided by 3 times 2x plus x squared minus 4 times 2/3 times x raised to the negative 1 divided by 3. A little crazy looking, but so we graph it, see what it does. We want to know the zeros. When does this thing cross the x-axis? Right? In other words, we want to know when does y prime equal 0? Well, now this is why they gave us that parameter at the beginning. We only want to look at x is greater than 0. So that means we're going to ignore this line and focus in right here. So what I want to do is I just want to find that 0 right there. So I'm going to plug in the 0 of the function, and I'm going to go to the left boundary, a little bit to the left of the intersection, a little bit to the right. Whoops. Let me clear off that marker. I can't see what it's saying. Let's try this again. I'm going to graph it. Second trace. Find the 0. And I don't know why. I think I double click or something. So I hit that. Left boundary, a little bit to the left. Right boundary, a little bit to the right. And somewhere in the middle. And I get when x equals 1, y equals 0. Okay, if you say so. So it's when x equals 1.
Yeah, really.
Right? So that's a critical point. So now what we need to do is we need to look at the original function. So I'm going to come back in here. Maybe there's some sort of boundary on the original function that I'm neglecting. Right? The extreme values happen in a couple of places. One, where y prime is equal to 0. We found that. That occurs when x equals 1. What's the other option?
Does not exist.
Where it does not exist.
0.
It doesn't exist at 0, right? So look at this. Watch this. So this process involves when y prime equals 0. That occurs when x equals 1. Another part of the process is when does y prime, when does that not exist? Well, look, there's a vertical asymptote here at x equals 0, isn't there? So we could say that another critical point occurs when x equals 0. That's what we have too. And then the endpoints of the function itself. Now, what we should do is due diligence and then do the last one, which is consider the boundaries of the original function f of x or y, or however the book defines it, or the test. So I'm going to turn that function off, and I'm going to come down here and graph the original function, which is x raised to the 2 divided by 3 times x squared minus 4, and graph it. And so our 2 points of interest are going to be 0 and 1. That's where our min and max might occur.
0.
And then it also said we're only interested when x is greater than 0, right? When x is greater than 0. So I'm going to totally ignore all this stuff. I'm going to ignore everything to the left of that. Well, I have a cusp at 0, and I can just find that by hitting trace and hit 0 when x equals 0, y equals 0. Is that a min or max? It's a relative max, right? It's a relative max. Now, what about when x equals 1? Y equals negative 3. What is that? It's a global min. That's the absolute lowest y value you would get based on the domain restriction that they've given us in the problem. Does that make sense? So, all right, now we kind of got our bearings there. We have a local max at 0, 0, and the derivative is undefined. I think it's this one, C, isn't it?
Yeah, that's what I said.
Yeah.